This particular event has been made possible through the partnership with Parkinson Society, Central and Northern Ontario, and Durham Region Chapter. And may I present Debbie Davis, CEO, Parkinson Society, Central and Northern Ontario.
That wasn't going to take very long. I just wanted to welcome all of you and thank you for coming today. We're thrilled to be working with the Durham chapter during this conference too. These education sessions are pretty key to what we do. We have normally in our region, we have about 4 or 5 a year. We try to spread them around. We actually had one in Thunder Bay this year that was a great success as well. We had 100 people come in April during a snowstorm. And so we were a little startled to have a snowstorm in April, but we made it through. So we're thrilled to be able to provide this, and I know a lot of work has gone on today, so I do want to thank the Durham chapter and the committee and our staff member, John Collins, who some of you met. He spent a lot of time on this as well. So we're just really great to have all of you here, and thank you so much for coming.
Thank you, Debbie. I want to acknowledge the members of the Durham Region Chapter who have been fundraising for years and years, and much of that money that we brought in through hard activities like selling raffle tickets, selling Christmas cakes, and all of that, much of that money is going to assist with this conference today. So I acknowledge all of the work that's been done up to and including today. You'll notice when you go to our lunch that we have balloons, and you might have seen them in the hall since the 30th. That's in recognition of our year. Now, a few housekeeping items. Homestead Senior Care has generously and graciously provided the services of 2 personal support workers today. They are Ashley and Cecil. And there's Cecil, and where's Ashley? She's in the hall? Okay, so that you see them. They are here to give you any assistance you may need during the day. So particularly if you need physical assistance, washroom, anything, help you get standing up, whatever it is, they're here for you for the entire day. The okay, some of these name tags are slightly pink in the background. They're all volunteers. But just for the moment, anybody who's a volunteer here today, please put your hand in the air. Well, all of those people, yes, all of the people on the committee, all of them. They're actually a lot of registration as well, so if you need assistance with anything, please ask. The washrooms, which is often the most vital piece of information you're going to need all day, are located at the back out into the foyer. There's a step this way, so actually behind this room, and a step down at the far end of the hall. Our intention is to provide you with information on Parkinson's and its effect both on the person with it and on their family. So to begin, I invite Sandy Jones, RN, Coordinator, Client Services and Education, PSCNO, that is Parkinson Society, Central and Northern Ontario. The rest of the day I'll just use PSCNO. To introduce Dr. Adams. I just want to say that Sandy is a gem. She is a person of extraordinary abilities and has given so much for so many years and continues to do so. So Sandy.
Thank you, good morning. I'm a little vertically challenged here. Whether I can do that. Okay. Well, this will definitely be too low for you, John. Okay. I'll just put this in here. I don't think Dr. Adams needs a great deal of introduction to many of you here today, but for those of you who don't know this gentleman, regardless of whether you are a person living with Parkinson's or a family member, your reaction to having heard the 3 words, "You have Parkinson's," will have been as unique and individual as everything else that has happened from that day to this one. From symptoms to rate of progression, response to medication, attitude, coping strategies, everyone in this room is different. One thing, however, that you all have in common is your quest for information, knowledge, and an understanding of What is Parkinson's? What are the current thoughts on treatment and management of this condition? And what is new in research to give us hope for the future? It is my pleasure to introduce Dr. John Adams, who will be able to answer these questions and bring you all up to date on the most recent information from the scientific world. Dr. Adams is a member of the multidisciplinary team of healthcare professionals at the Center for Movement Disorders in Markham. While he may look like just an ordinary guy, John is actually one of a rare breed of neurologists known as movement disorder specialists, of which there are only about 45 in all of Canada. John graduated as a Doctor of Medicine from Queen's University in Kingston in 1998, did his postgraduate training in neurology at the University of Western Ontario in London from 1998 to 2003. From 2003 until 2005, he was a clinical research fellow in movement disorders at the Pacific Parkinson's Research Center in Vancouver. Did I get it right? I always screw up. In 2004, John received a Basic Research Fellowship Award from Parkinson's Society Canada, the funds from which came from your hard-earned Superwalk dollars. For the past 6 years, he has been a staff neurologist at the Center for Movement Disorders in Markham, and I think you will agree that John is well qualified to give us an update on the most recent understandings about this very complex condition we call Parkinson's. Please give a warm welcome to Dr. Adams.
Thank you very much for asking me to come here. It's always fun to do these kind of things. All right. Just so you know, that Basic Research Fellowship, we studied familial Parkinson's disease, inherited Parkinson's disease. And the bottom line from the stuff we ended up publishing from that was that you can detect changes associated with Parkinson's disease many years before the clinical signs show up, not using PET technology. We have a family with late onset Parkinson's disease, and we tested young girls in the family, the daughters of people affected in their 20s and 30s, the early signs of dopamine loss and stuff like that. So that's what we were dealing with at the time. Anyway, but today we're talking about something different. I know it was earlier this week that I finally looked at the brochure. And and then I think Maddie called me, but I don't know what she said. So I was speaking out, she's like, oh, this is more about the family and all the, stuff around that. And I had no idea what to talk about there, so I said, I can't talk about that. I don't know anything about it. That's not quite true, but I know I didn't read it. Anyway, so my topic isn't exactly, I don't think, necessarily fitting with everything else in here, but what I wanted to do actually was talk about what people keep asking when they come to the clinic, recent things in the media, right?
Excuse me, we're not hearing you well back here.
No, this thing's too bad. Can you hear me now? I have to reach over.
Well, it's going back and forth, I think, when you're moving.
All right, I'll have to try and sit right in front of this thing then, okay? It's going to be hard though, because I kind of move around. So, objectives then, just recently reviewed Parkinson's disease-related topics as seen in the media or elsewhere. Let's see how far we get. Okay, so what's that? We can't say it, I'm not going on. What is it? So that's dopamine, right? So you do, okay, see, now I'm going to have to do this. Doesn't this look like a sad guy going dough? And then there's that old part. And then, of course, that little NH3 up there is the amine, so it's dopamine inside function. It's got nothing to do with the topic, so it's interesting. Any more familiarity with this one? I like this guy because this chemical looks like this. Alright, that might be a bit better. Anyway, okay, so this thing looks like a dog, right? Its back legs up, but it's a dog. Anybody know what that is? Again, it's got nothing to do with dog. It's alcohol. It's the only thing that can build on my organic chemistry stuff. Okay, but this is actually what I want to talk about first of all, okay? Anybody know what that one is? Come on, where have you been? It's ibuprofen, also known as Motrin, also known as brings me to headline number 1. Ibuprofen tied to lower Parkinson's risk. Anybody heard about this? This is on CBC News, which comes out in March 2011. And lots of other people, of course, reported it as well. So what's it about? Well, it's about, don't freak out, it's about that paper there. This is the abstract. You're not supposed to read it. You can't go on. But this is the actual article, just so you know, Clinical Neurology in March 2011. Use of ibuprofen and the risk of Parkinson's disease. So what's all this about? Okay. So here, this is a study. One of the problems in the past has been, when you're trying to figure out what risk factors are for Parkinson's disease, you kind of do these retrospective studies. You go, well, how much tea did you drink, or how much coffee, or what did you smoke, or this, that, and the other, or where did you live? And it's always got recall bias. It's hard to remember everything. So you want studies that move forward, so prospective studies, groups of people, cohorts as they call them. And there are many of these, or several of these around now, with over 100,000 or more individuals, often nurses, physicians, and others. But so we use these people, and they took information dating 1998, 2000, and every 2 years they send out questionnaires and get feedback, and they have a very good response rate. So they follow these people over 6 years and said, well, how many people have developed Parkinson's disease in that time, and how are they different than each other, right? So basically, over the 6 years in this particular study, 291 people developed Parkinson's out of 136,197 that were actually followed. And what they found out when they looked at this is that the people that used ibuprofen on a regular basis, and I'll come back to that, had a lower risk of developing Parkinson's disease compared to those that did not use ibuprofen on a regular basis. And ibuprofen being regular was at least twice per week. And the more often you took it, the lower the risk. And that looks like a 38% reduction in risk. That did not pan out for aspirin or Proxen or any other anti-inflammatory nor Tylenol. So there seems to be something kind of specific about ibuprofen here that's worth following up on. Right? So they went one step further. They did something called a meta-analysis. What that is, they basically go and find any study that fits very robust criteria and pool everything together and find out how many, does this thing make sense, and look at everybody's studies. And so they had about 12 additional studies combined with their own, and they got a similar, not too far off, risk reduction, right? So relative to 0.73, which basically gives you a 27% less risk of developing Parkinson's disease if you're taking a fair amount of, or some degree of ibuprofen. Which I'm assuming they were 200 milligram tablets, we're talking about twice more a week, and these things were all controlled for other variables. So it's kind of neat. So why ibuprofen? I mean, it wasn't other anti-inflammatory, so the suggestion is that it's not an anti-inflammatory thing necessarily. There's a bunch of other little studies out there on animals and such, and there's something about ibuprofen that stimulates some kind of chemical, PPAR gamma. I have no idea what it is, I can't remember what it means, but the point is, this thing has something to do with cell death, and by affecting it, it reduces the amount of cell death. So there may be actual rationale behind this, right? So it means protect against cell loss. And actually that branches out into things like Alzheimer's as well, same kind of thing. So the problem is, so basically what these guys said, if you're taking a bunch of ibuprofen, your risk of developing Parkinson's disease may actually be less. But it doesn't say what happens if you've got Parkinson's disease and you take a bunch of ibuprofen. I mean, ibuprofen does have side effects, right? You've got like high blood pressure and hemorrhaging and bleeding and whatnot, so you do have to take it with a grain of salt. So basically you need more work on that. We need to see what that means. But just to put it in a bit of perspective, and not to put too much down on it, this sounds really good, 50% risk reduction, right? But the actual risk of developing Parkinson's study was 0.2%. That's 291 into 136,000. So your risk, instead of being 2.2%, is 0.13%. So it's less impressive when you look at that. All right, headline number 2. Unfolding pathogenesis in Parkinson's. Breakthrough suggests damaged proteins travel between cells. The Science Daily News and others back in January. Pathogenesis, CAR, is another word for CAR, right? So what's this all about? No, it's not a self-portrait. Does anybody know what that is? It is a mad cow. Exactly. Mad cow as in mad cow disease, right? No, Parkinson's isn't the same as mad cow disease. I don't want to go there, but this brings up a point though, right? So the other name for mad cow disease was bovine spongiform encephalopathy, as you know. And in other animals, you get mink encephalitis, scraping in goats and sheep. And if if that disease, the cow one anyway, gets into humans because you accidentally consume some affected beef, then you get this new variant Creutzfeldt Jakob disease. That's what we used to call it in humans. That seems related. You're all familiar with these people from Papua New Guinea, right? They have the ritualistic cannibalism where they eat the brains of the people that died in their tribe as part of their usual rituals. And when they get, basically they were infecting themselves with another one of these type of diseases, and they're giving themselves something called kuru, where they would get very ataxic and demented and so forth. And then there are other examples of these kind of diseases. Gerstmann, Strauss, Slanker, you all know. And one of my other favorites, familial fatal insomnia. Sounds pleasant. Anyway, what do they all have in common? These are prion diseases, or prions, some people will call it. Anybody heard of prions before? Oh, okay, tell us what. They're proteinaceous infected particles, exactly. So what we're getting at here is infection. Usually we think that's a virus or a bacterium, a fungus, a parasite, something like that, that gets into our bodies and sort of takes over temporarily, right? An infection. Usually by, it's something to do with RNA and DNA and et cetera and so forth. But proteins can kind of act in the same way. They've got no RNA or DNA or any genetic material at all. And what happens in these diseases, and that last page describes a whole bunch of them, is that you have a protein, in this case it's the PRPC, that green fellow, that he's normal and fine, or he or she, but something happens, maybe it's an insult, maybe it's like an environmental insult, or it's a genetic thing, or it changed into a red, angry, square protein, one that's not happy, it's abnormal. And in these diseases, though, what happens is, this bad protein goes back and makes all the good proteins bad too. It's like a bad peer pressure thing, right? And it's a vicious cycle. You get more and more of them, and they start sticking together, they start clumping, and you get like plaques of protein aggregation, right? So that's one thing. So your protein makes other proteins nearby bad as well, and the cycle continues. So it brings up this again. No, please don't try and read it all, but I'll just show the actual headline. Lewy body-like pathology. Right, so we're already familiar with Lewy bodies. Lewy bodies are those little collections of proteins that you see in damaged Parkinson cells. So it's the hallmark, if you will, right? All right, so you can find those in long-term embryonic nine-growth transplants in Parkinson's. Well, what does that mean? Okay. This is related to, I don't know if anybody here was involved in this, but probably not this day, but about 15, 16 years ago, they wanted to try doing fetal midbrain transplants to help Parkinson's symptoms, right? So they would take fetus, take the midbrain, which is where the dopamine cells predominantly are, mix it up, if you will, in a tube, and then inject it into the brains of individuals with Parkinson's disease, just as we see across the top here, right? And what happens, these things actually work. The grafts, as they were called, these cells that were donated in, grew and they produced dopamine and had a symptomatic effect. But one of the big problems was that they had some people had severe dyskinesia even without medication. So they needed brain surgery to fix the dyskinesia and so forth. So anyway, but there was some big lessons learned there. But what's happened now is that 14 years later, some of these people have passed on and donated their brains to continue the search for a cure, if you will, or at least more information. And what they found was that in their natural, this is the person themselves, okay, this is their natural cells. They have Lewy bodies, as one would expect, to confirm the diagnosis of Parkinson's disease, right? But in the graft cells, so these are the ones that came from the fetal midbrain, they also have Lewy bodies. So that's the tissue coming from somebody else. So it suggests that when you put these cells in there, they start getting pathological changes as well. So how does that happen? Well, that's going back to this again. Sorry about this sort of funny looking slide. Ignore the left side for now. But so basically, what they're trying to suggest is that if you put this is like the host cell. Don't worry about donor cell recipients. Talking about something else, but this is the bad cell, right? In the person with Parkinson's, it's got its funny looking alpha-synuclein. Alpha-synuclein is the protein in the Lewy body, right? So this is the funny protein in Parkinson's. And you can get out of that cell and go into a new cell, i.e. from the donor, from the transplant, and take the normal alpha-synuclein and make it a bad one too, right? So that's one theory as to why the cells that were donated started looking like they had Parkinson's too. So remember this diagram, what we added this in now, right? So there's alpha-synuclein, which makes the Lewy body, the protein in Parkinson's is one of the main factors, right? It gets converted to a nasty alpha-synuclein, a bad one. And then that one keeps going back here and it starts accumulating and you start getting Lewy bodies. So the theory is then that one theory behind here is that the alpha-synuclein, once it's damaged in one cell, then it will infect the next cell, and the next cell, and the next cell. So this is only a theory, a hypothesis, right? But it could explain this. And this is a hypothesis by someone called Heiko Brack. And this is pathological changes, and they came up with this idea that Parkinson's disease spreads. Right? The pathology spreads, and that could fit with this clinical science. So what they're saying basically is this. Parkinson's disease pathological findings in the Lewy bodies are first seen in the bottom of the brainstem here, and here in the olfactory or smell centers, if you will, right? And over time, they spread up, and then through the rest of the brain. So spreading, that would fit with this one cell to the next protein spread, right? So that actually might make some sense. If it starts here and here, right, that's maybe loss of sense of smell, constipation. You come up here, maybe you get restless legs or anxiety, depression. And once you get to here, you start getting slow and tremor, right? So this process is going on well before we get the symptoms that we normally make a diagnosis on. That's stage 3 of pathology. Anyway, so that's one theory. Just on another note, though, it's important to know at this point in time, although the brain is obviously affected in Parkinson's disease, it's quite clear now that it's not just a brain disease. Right? You can find the Lewy body changes in other pathology in the peripheral nervous system, even down in the nerves and around organs in the body. So the whole thing is involved, all right? One last thing then. So, so why would these areas be the first to be affected? Or what if something got in this way and got and set the process off, or something got in the guts and got in through the gut and then tracked back up in there? All kinds of things. But I think it's a very interesting thing. You should follow up. All right. Those are rhetorical questions. All right. Okay. So headline number 3. So was gene therapy, right? Offers hope for Parkinson's disease. Small trial improves patient symptoms. Nature News, March 2011. And there's the paper. Quickly take that down. There's going to be a quiz. Anyway, but again, the purpose is really just to show that this is the actual paper. It's not something made up by the media. There's really something out there. So this is talking about gene therapy, taking genetic material and using it to modify what's happening in the brain to make the Parkinson's symptoms better. Okay? So let's see where that go. All right. Yeah, let's do it this way. Again, sorry about this complication, but really just focus on what I'm going to point out to you, really. Normal at the top, Parkinson's disease. This is the basal ganglia. This is a very simplified version of what may be happening in the cellular level. But just look at this real quick. So that little part right there, SNC, substantia nigra. Red arrows is dopamine. That's nigrostriatal. That's where the main problem is in the motor component, right? In the midbrain of Parkinson's disease. Look at this STN there. And then look at thalamus and the rest of the brain. Those are the only ones I care about here. In Parkinson's, down here at the bottom now, right? Look, the little skinny red lines. Not enough dopamine. And what happens is this shuts down this pathway, but it cranks up this pathway, okay? Including this particular area, the subthalamic nucleus, which cranks up its output. And that makes the output to the thalamus much higher. And look how skinny the little yellow lines got here now, right? So the output to the rest of the brain is inhibited. Everything slows down. That's very simplistic kind of thing, but I think it's a useful model, right? So subthalamic nucleus, just so you know, if you end up going for deep brain stimulation right now, that's what we're aiming for, okay? But that's exactly what we're aiming for in this study as well. So, when this thing is overactive, it's producing something called glutamate, which is an excitatory amino acid. It's like the brain's own speed, if you will. It cranks things up. Its opposite is GABA. Okay, GABA is what slows you down. GABA medicines like clonazepam or lorazepam, these calm things down, right? Oh yeah. So what these guys did was said, can we convert that subthalamic nucleus from instead of cranking up the glutamate, being overactive, slowing it back down again? And what they do to do that is the glutamate, to convert it to GABA, you use something called GAD, or glutamic acid decarboxylase, right? So you want to get this enzyme and jam it in where you want it, right? And that's what they needed to do. So what they did is they took these viruses, okay? And if you ever ask me what's the name of the virus, you say, I don't know. because that's what it is, adenovirus. So it's adenovirus, and they take the gene, obviously they make it so it doesn't give you the common cold, because that's one of the common cold ones. And they take this gene, right, that's a little DNA signal at the top, and they shove it in there. And then they take those viruses and they implant them in both sides of the brain into the striatum, right, where there's no dopamine. Sorry, it's in the subthalamic nucleus where we want it, right? And viruses do, they infect the cells that are there, and the cells then crank out all this extra GAD. And when they do that, right, there you are, just so you know, the brain looks like the brain. This is like where they put it right here in the subthalamic nucleus. You recognize the subthalamic nucleus there? Right, just above the substantia nigra, sitting right below, which is where, of course, the dopamine problem is. And basically, they try and convert the glutamate to GABA. What they found was, so this is a double-blind study, meaning that no one knew what each person was getting. That's one of the keys about any kind of research. We'll see that in a minute. So they had sham surgery. Some people got the surgery, but nothing was ever implanted. So everything was actually the same, they just got nothing. And they followed for 6 months. So 22 people in one group, the one who got the GAD, this new gene, enzyme, and 23 got nothing. Anyway, the point here I'm making is, these guys showed 23% improvement in the motor symptoms versus a 12% improvement on the guys that didn't get these genes. So basically, there's like, there is an improvement in the motor symptoms in the people that got this gene. So it shows there's promise for gene therapy. This is without medication. So their symptoms were better without medication. This is only a small study. This is a preliminary study. It needs to go on to the next level, but it's very promising. Okay. So peripheral brain stimulation is a terminology that I've only recently come across. I think it was about 10 o'clock last night. But it's to do with something, this is a term I think that's coined by Dr. Worth of the Parkinson Center. And it discusses a type of permanent acupuncture using titanium implants in the ears. Have you guys come across this one yet? Because people are coming in and asking about further. So I thought, well, we better look into this and find out what's it all about. So, okay, these are the actual titanium implants here, right? And of course, this is what they're focusing their therapy on, a homunculus, a representation of the human body in the ear, right? This is sort of the basis, I gather, part of my English on it, of acupuncture. So it's based on that, of course. All right, so what's it all about? Well, Dr. Worth, on the internet, if you Google him up, there's actually a paper there, and he describes step by step how he came up with this particular type of treatment. And I'll just go through it, and I obviously have an opinion on it, but his first observation was a woman that came into his clinic with trigeminal neuralgia. That's not like, they call it the suicide disease, where you've got like such severe shooting pain in your face, like you basically want to rip your face off, or you'd rather die than actually go through the pain. But anyways, it is what it is. So trigeminal neuralgia, and basically he stimulated, he pressed on the point on the ear representing the trigeminal nerve very specifically, and he shoved in one of these titanium implants, and his quote says, "I pushed harder than usual." And then she went away, and her symptoms completely resolved, and then she came back, and he felt that the little plug was still there. She didn't know the plug was there. In other words, he did it without actually telling her, from what I can gather. But anyway, when he took it out, the pain came back. So that was his first observation. Then the second observation was that he had a friend from World War II that 50 years ago got a piece of metal in his ear from the war. And he realized that, it stayed there the whole time and it didn't move and it wasn't affected. He said, okay, well, that makes it probably safe. Then another fellow did the same thing. He did knee arthritis, went to the area on the knee, represented on the ear, and put in the implants, and the guy came back 2 weeks later with no crutches. So that was his second observation. And then he did another trial comparing acupuncture routine versus these implanted titanium plugs. And he treated hypertension, obesity, smoking, alcohol, pain syndromes, allergies, depression. Basically said the permanent implanted titanium plugs were better long-term efficacy than just doing acupuncture repetitively. I gave you a sustained response. So that was the strategy behind it. So then he basically saw one person with Parkinson's disease and tried treating him and got some improvement. So then he went on to do a series, right, of uncontrolled studies. And so what he did was he chose, according to his words, the substantia nigra region on the ear homunculus. Well, substantia nigra is like that big in a full-grown adult, right? I don't know how you represent it, or some of it, I don't know how that works, but anyway. And then he basically treated 28 people in a row, and this is his research protocol, was to ask them these questions. Did you get the chance to reduce your medication? Is your movement better? How's your mood? Has your shape decreased? Is the constipation less? And how is the quality of life improved? And he got a 90% improvement rate. Didn't say by how much or anything else, and of course there were no controls and so forth, right? But he recognized that he needed to do more work in an external study, of course. That makes sense, right? So what he did here was he approached someone in a clinic in Germany, Parkinson's clinic, and said, can you test this out in your clinic? And so he took 20 people, it didn't say how they found them, and basically stuck the implants in 20 people and then followed them over about 12 weeks. And then basically what he shows is that when they use the UPDRS, which is the main scale for recording changes in Parkinson's disease. It doesn't specify whether they're using type 1, 2, 3, or 4 parts of the scale. Number 3 is the motor scale, which we often use. But anyway, he showed that this was the summary. There were improved curves, and 80% won a better quality of life. No controls, no methodology, no selection. We don't know anything about it, but that was the proof at that point. So I thought, well, I better look at this up in the literature. I did this actually about a year ago, and I did it again just the last couple of days, just at the absolute show. So you look at PubMed is your resource, is the resource for all medical knowledge from, if you want to, Western medicine, you want to call it that, right? Now I'm to it, stuff. When you look at Parkinson's and acupuncture, you find about only 75, I'm a bit surprised, only 75 papers published since 1947. And most of them, or many of them, are on animal models. But there are a couple of reviews, systematic reviews, where they look through the data and try to compile it all together. And there was some quasi, benefits from acupuncture. Again, it's really hard to control acupuncture trials, right? Did you get acupuncture or not? Like everybody knows they got it or not, right? So very difficult to study. But as I looked up Parkinson's and acupressure, there was nothing. I looked up Parkinson's and titanium implants. There's no evidence or research at all. I looked up Parkinson's and permanent acupuncture, 0. So I looked at Parkinson's and Worth, right? And there's one study, but it's not him. It's somebody else talking about narcoleptic-like symptoms in Parkinson's. When I Googled Dr. Worth himself, I didn't find anything. So nothing actually got published in sort of mainstream literature. I believe if you look on his website, they do have, he reports magazine articles and a few other things like that. And as you may know, there's now someone doing it in Vaughan, right? She's got, so they call it a worldwide Parkinson Center now, and so Vaughan's got one, Ottawa's got one, Cancun, Malaga, Valencia, and someone else, perhaps Germany. So anyway, it's out there, and I'm not saying that it doesn't work, right? I mean, what I mean is, people come in, this is an expensive treatment. So, my thing is like, if it's proven, go for it. If it doesn't harm you and it's not expensive, etc., go for it. But if there's like no evidence and it's really expensive or there's a potential for harm, I think you have to really look at the details and see what this is for you. It's the same thing with stem cell treatment, right? You go off to the Caribbean or China and pay $20,000 for stem cells, they put them in your spinal canal or into your veins, and there's zero evidence for that nowadays. I mean, there's a lot of research coming along, that's great, but it's your choice, but I sort of say so quickly, because I'm short on the time a little bit here. Headline number 4, the Parkinson's power switch was located. This was actually back last October. Now this is this was a really hard paper to actually get, so I don't have the actual, I lost it. I don't know where it is, somewhere. I only get a paper copy, but nonetheless, the point being is, I don't even remember this, but a little while ago, I guess October, they came out with this thing saying there was a breakthrough in Parkinson's, this gene was found. And what they did was, like I said, I find it a really hard paper to read because I'm not smart enough, I guess, but the gene, what they're looking for is genetic material, something that makes Parkinson's tick. What's going on here? But rather than look for select genes, right, they did this kind of program where they looked at groups of genes that made sense, that work together, right, as a circle. And they found a group of, several groups actually, but one group in particular that seemed to correlate with Parkinson's disease. And all these, the genes were turned off. And all these genes had a master gene switch. So they were on, this was called this PGC1 alpha, the peroxisomal percolator activator receptor gamma coactivator. Anyway. But the point is that, so this looked like a master gene switch, and the question was, like, if you flip that on, do all the other genes turn on, right? And this is a gene that's associated with the mitochondria. The mitochondria are little parts of the cells that generate all the energy. furnace, if you will, some people refer it to. We know the mitochondria are affected in Parkinson's disease. That's well known, actually. I mean, it's one of many, but that is a main part of Parkinson's disease, the damaging cells in mitochondria. For example, you can take rotenone or other pesticides and they will damage that exact area and cause Parkinson-like symptoms, right? The guys that were making synthetic heroin in California a number of years ago, they got that byproduct, and then they took their product, that they all gave themselves Parkinson's disease, right? So, and then that particular MPTP actually is now used as animal models to generate, for study, for research. Anyway, so we know the mitochondria involved. The pesticides is the most common environmental link. But this gene may have something to do with it. Now, they didn't actually prove that this gene is turned off or on, but there is a link to the other one. Anyway, so that's what that was about, this master switch. And I think what was really intriguing is that this is not the first time people have looked at this gene. In fact, it's been around for a while, but there's a medication used in diabetes called Actos, and it actually modifies, basically turns on this gene. So there are already medicines out there. But anyway, something to keep an eye on, right? Something else that looks promising. All right, so a little bit late breaking news. This actually isn't today's breaking news. This actually isn't very good news, I suppose. This is about coenzyme Q10. And back in 2002, a study was published looking at coenzyme Q10 and whether or not it modifies symptoms of Parkinson's disease. And this was about a 16-month trial. We looked at 4 groups: people who received nothing, placebo; people who received 300, 600, 1,200 milligrams a day of coenzyme Q10. And they followed them with a series of criteria, but one again was this UPDRS, the Unified Parkinson's Disease Rating Scale. This was the total scale. I think that's about a measure of 180 odd or something like that. And what they found was, over the course of this, that the symptoms, if you will, by the UPDRS got worse by a score of about 12 if you're on placebo, about 8 or 9 if you're on 300, 10 if you're on 600, but only 6 if you're on 1,200. So the higher the score, the worse your Parkinson's symptoms are, right? Like death, I guess. So what it suggested, there was a trend towards less disability. That was their conclusion. And it makes, 300 seems to be better than 600, but 1,200 is better than both 300 and 600. So it needed more study. That was the bottom line, right? So when people come and ask me, what's the deal with coenzyme Q10? I said, well, there's a trend there, but we need more evidence. 1,200 milligrams of CoQ10 is pretty darn expensive. So, all right, so they did the QE3 study, and they're looking up to 2,400 milligrams a day, looking to see whether or not this actually was beneficial. And just sort of through the grapevine, it's not public knowledge yet, but unfortunately that study failed to meet futility criteria. So coenzyme Q10, according to this, and we'll get the official notice, does nothing. So that's the newest piece of the information. Not great, eh? So, but anyway, I think in summary though, I think there's some promise. I really like the idea of this prion concept. And no one's going out there saying, it's mad cow disease, and that's not the message to take away. But the style with which, or the way in which those things propagate may be very useful, because then there are potential avenues to treat, right? Block this alpha-synuclein, the antibodies to it, something like that, right? So I think that's really promising. Gene therapy looks very, very promising as well. Some disappointment with the coenzyme Q10, which of course works in the mitochondria. I think it's too small a thing, right? I mean, we need to look at a bigger picture than that. But there's definitely progress being made there. And so I think that's it's useful. I think things are just coming along. Okay?